The foveated extrapolation framework is the first to address the ambitious task of very wide video extrapolation and the first to provide a feasible solution tailored to this task. Wide extrapolation for peripheral vision has several applications. While the viewer is aware of the true data region, we aim for video expansion that enhances the sensation of being embedded in the scene. For instance, instead of viewing a white wall around the television set, extrapolation may offer a relevant extension of the scene using novel display hardware. Typical web video is of low resolution. Extrapolation may provide a relevant background instead of distracting clutter. Video extrapolation may be integrated in microdisplay systems where video is projected directly into the viewer's retina. Many image and video completion algorithms exist. To fill in small holes, good results are obtained by patch-based methods. Such methods, however, do not lend themselves easily to very wide extrapolations. The chance for artifacts grows as the synthesized regions become more distant from the domain of the raw video. Note the distracting artifacts in the periphery. Moreover, processing time becomes unreasonable. As a first step, we revised the completion algorithm of Cremonesi et al. To reject source blocks with distracting features in peripheral completion. Although the number of artifacts is reduced, they are still common, and the processing is still too slow. Addressing these two problems, we introduce a solution that exploits the foveated nature of human vision. Let the extrapolated region project outside the viewer's fovea. Then the synthesis process can use patches that become gradually coarser and significantly fewer, following the natural resolution fall-off of peripheral vision. We show that this approach significantly increases the chance for a result free of attention-drawing artifacts, and it leads to significant runtime acceleration. Foveated video extrapolation works as follows. The raw video is spatially extrapolated at full resolution to some extent. Then this intermediate result is scaled down and further extrapolated at a coarser scale. Again, the intermediate result is scaled down and further extrapolated. This is repeated until the entire required domain is filled. Each intermediate result is magnified to the physical display pixel units. The final output is constructed by feathering relevant intermediate results in each spatial location. We stressed that this is a general framework. The extrapolation at each scale step can be considered as a black box, and thus a wide range of completion algorithms can serve as its engine. In our implementation, the engine is the completion method mentioned before, the one that rejects peripheral distraction. For best illustration of the foveated extrapolation results, it is recommended that you use a large display and sit relatively close to the screen at about half screen width distance. Recall that the viewer is aware of the input domain. Since it carries the real information, the viewer would usually fixate on this domain, considering the expansion as an enhancing feature. The MATLAB processing time was reduced from several hours per frame to a few minutes per frame. This example demonstrates a failure case where the periphery exhibits distracting motion. Here, a completion engine that incorporates camera motion analysis may help. Foveated extrapolation can also be applied to still photography. Thank you for your attention.